Here is a cubic equation. X cubed equals 15x plus 4. You can see the answer. It is 4. 4 cubed is 64, and 15 fours plus 4 is also 64. Done. Now watch what happens when you try to get that answer the only way anybody in 1545 knew how. Because the formula reaches 4 by going through the square root of a negative number. And that is not a trick or a shortcut. There is no other route. Let us deal with the name first, because the name has done real damage. Imaginary. That word was picked by René Descartes in 1637, and he did not mean it kindly. He meant, these are not real quantities, they are things we imagine, and you should not take them seriously. The label stuck. The mathematics carried on working anyway. So 4 centuries of students have been handed a subject whose own name tells them it is made up. And it is not. Everything in this video is as real as the number 3. It just turns instead of counting. Here is the story you were probably told. X squared plus 1 equals 0. Rearrange it and you need a number that squares to give -1. There isn't one. So mathematicians invented one and called it I. That story is tidy and it is wrong. Nobody invented anything because of that equation. Look at it. The curve sits above the axis and never comes down. There is no crossing, so there is no solution. And that is a complete answer. You are allowed to say there isn't one and walk away. And for centuries, that is exactly what everybody did. The trouble came from somewhere else. It came from cubics. In the 1540s, Italian mathematicians finally cracked the cubic equation. General method works every time, the same way the quadratic formula does. It was the biggest result in European mathematics for centuries, and then somebody pointed it at this one. The method goes like this. For an equation of the form x cubed equals px plus q, you compute a quantity from p and q, take its square root, and the answer falls out of 2 cube roots added together. For our equation, p is 15 and q is 4. So, half of q is 2. Square it and you get 4. A third of p is 5. Cube it and you get 125. And the formula wants the first one minus the second. 4 minus 125, minus 121, and then it wants the square root of that. This is where Girolamo Cardano stopped. He hit exactly this in his book in 1545, wrote that the whole thing was as subtle as it was useless, and moved on. Which is a completely reasonable response. He is being asked for the square root of a negative number, and there is no such thing. Except that the equation he was solving has an answer. It is 4. It is sitting right there. 27 years later, Raphael Bombelli looked at the same problem and had what he himself called a wild thought. What if you just carry them? Do not ask what the square root of minus 121 means. Write it down as 11 of some new thing. Follow the algebra and see where you come out. So the formula is asking for the cube root of 2 plus 11i. Bombelli guessed it might look like 2 plus I and checked. Cube that. 2 cubed is 8. Then 3 times 4 times I, which is 12i. Then 3 times 2 times I squared, and I squared is minus 1, so that is minus 6. And finally I cubed, which is minus I. Collect them. 8 minus 6 is 2. 12i minus I is 11i. 2 plus 11i. It works. And the other cube root is the same thing with the sign flipped. 2 minus I. Now add them, because that is what the formula told you to do. 2 plus 2 is 4. And I minus I is nothing at all. The imaginary parts cancel exactly, and you are left holding the number 4. Stop and look at what that was. You started with a real equation. The answer was real, and whole, and visible from across the room. and the only path from one to the other ran through a quantity that supposedly does not exist. You went somewhere impossible and came back with something you could check. That is not a bookkeeping trick. Something is there. So what is there? Here is the answer, and it is much simpler than the name suggests. Take the number line. Multiplying by -1 sends 3 to -3. We usually describe that as flipping the sign, but look at it on the line and describe it as a movement instead. It is a turn. Half a turn, 180 degrees, around 0. Now here is the question that opens everything up. If multiplying by -1 is half a turn, is there something you can multiply by twice to get the same result? Something that does half of the half turn? There is nowhere on the line for it to go. A quarter turn takes you off the line entirely. And that is I. Not a number we invented to plug a hole. An operation. A quarter turn. Do it once and one lands up here. Do it again, and you have turned 180 degrees, which is exactly multiplying by -1, which is why I squared is -1. It is not a rule you have to accept. It is just what turning twice does. And it closes. Turn again, and you are at -I. Once more, and you are back where you started, at 1. 4 quarter turns, 360 degrees. The powers of I go round in a circle because that is literally what they are doing. Once you allow a quarter turn, the line cannot stay a line. There has to be somewhere for it to point. So the number line grows a second direction, and every number becomes a place. 3 plus 2i is not a strange hybrid object. It is a point, 3 across and 2 up. And now multiplication becomes something you can watch. Take 3 plus 2i and multiply it by 1 plus 3i. Do the algebra and you get -3 plus 11i, which on its own tells you nothing. But look where those 3 points are. The first one sits at an angle of about 33.7 degrees from the axis. The second is at 71.6. Add those. 105.3. And that is exactly where the answer is. When you multiply two complex numbers, their angles add. And the distances multiply. The first point is 3.6 from the origin, the second is 3.16. Multiply those and you get 11.4, which is exactly how far out the answer sits. So multiplication is 2 instructions: turn by this much and stretch by that much. That is all a complex number is, an amount of turning and an amount of stretching. Here is the part I find hardest to forgive. That picture, the plane, the turning, all of it, was published in 1799 by a Norwegian surveyor called Caspar Wessel. He got it completely right. And nobody read it. It sat unnoticed for about 100 years. 7 years later, Jean-Robert Eigen, an accountant in Paris, worked it out again independently and published it himself. That one caught. It is why you will hear the complex plane called an Argand diagram, which is a little unfair to a Norwegian surveyor. Gauss, who had known all this for years, went further. He said the whole problem was the vocabulary. He suggested we should have called them lateral numbers. Sideways numbers. Positive, negative, and lateral. Imagine being taught that instead. Nothing about the mathematics changes, and the entire sense of it being a fiction just evaporates. Look at the gap this all sits in. Cardano hits them in 1545. The correct picture is finally drawn in 1806. That is 261 years of people using these things successfully, while insisting they were not really there. And Descartes names them imaginary in 1637, 169 years before anyone drew the picture that would have shown him he was wrong. Now, usually this is where a video tells you that engineers use complex numbers for alternating current and signal processing, and that they are terribly useful. And that is true, and it is a weak defense. Useful things can still be fictions. A convenient bookkeeping device is still a bookkeeping device. So here is the strong one. Quantum mechanics is written in complex numbers. For a long time, you could argue that this was just convenience, and that you could rewrite the whole theory with real numbers if you were willing to be clumsy about it. In 2021, a group of physicists showed that you cannot. A quantum theory built from real numbers alone makes different predictions from the ordinary one. Not clumsier, different. And within a year, 2 separate experiments went and measured which was right. The real one lost. Every kind of number we now use was somebody's absurdity once. Negative numbers were rejected as debts pretending to be quantities. Irrational numbers broke the Pythagoreans badly enough that there are legends about it. 0 took centuries to be accepted as a number rather than a gap. Each time, the objection was the same. That is not a real thing. It is just a device that happens to work. And each time the answer turned out to be the same as well. If it survives every test you can put to it, at some point you have to admit it is describing something. They are not imaginary. We just called them that and never took it back. Every figure in this video was computed rather than remembered, and the sources are in the description. If you want to see where this goes next, there is a video on Euler's identity, which is this same idea taken one turn further. Thank you for watching. If you would like more of these, subscribe.